Welcome to the Proteomics in Proximity podcast, where your co-hosts Dale Yuzuki, Cindy Lawley and Sarantis Chlamydas from Olink Proteomics talk about the intersection of proteomics with genomics for drug target discovery, the application of proteomics to reveal disease biomarkers, and current trends in using proteomics to unlock biological mechanisms. Here we have your hosts, Dale, Cindy and Sarantis.
Hello everybody, welcome to our episode dedicated to biomarkers of heart failure. I welcome with me today Dale and Cindy.
Hey.
Hey there.
And today the paper that we'll discuss is about the protein biomarkers of new onset heart failure, and is published in Circulation Heart Failure Journal. The first author is Nicholas Zero, and the last author is Professor Fayez. The most important finding of this paper is the use of proteomics and Olink Proteomics in order to identify biomarkers related to heart failure. And it's an amazing study looking in 3 independent cohorts, ERIC, FHS, and HOMAGE. And the finding was dedicated to, let's say, proteome secretome, and biomarker discovery connected to heart failure. Cindy, would you like to give us a little bit of background of these cohorts and some of the characteristics of these cohorts that they have studied? Thank you.
Sure, absolutely. So I'll give them, I'll just summarize them in order that they are in the title. So the Heart Omics and Aging cohort is the HOMAGE. It's actually a consortium, an EU-funded program, and they're looking for personalized strategies for, understanding cardiovascular disease. This is a consolidated effort among 8 European countries. I mean, this is just a massive undertaking, right?
So they have 8 different countries looking at heart omics and aging. So the two are together?
Yep. So both, yes, together. So, but within this subset, there's 3 represented groups. So there's something called Predictor, Health ABC, and Prosper. And that's from a subset of samples from within 20,000 that are this combined consortium.
Wow.
That represents HOMAGE. Yeah, it's pretty. I mean, when you start digging into these cohorts, it's just awe-inspiring what is able to be done, bringing collaboration together. Right.
So HOMAGE is roughly
impressive.
20,000 large, or even larger. Oh, it is.
That's right. 20,000 large. Yep.
And these are.
And then there's a subset that are represented within this study.
I see.
So I think the HOMAGE, they had 562 individuals in this study that were cases. And again, those were identified, as Sarantis mentioned, incident heart failure. So the characteristic was that they were diagnosed and hospitalized, but not necessarily, or they would have been excluded if they had been identified with heart failure coming into the study. So the importance there is to be able to more likely identify the markers that are linked to predictive value in predicting heart failure likelihood, rather than, and we're trying to, tease out the pathogenetic biomarkers, right? Over time with these studies, we're trying to understand what's predictive and what's incident, what happens after you have this diagnosis.
So for the HOMAGE study, then they ended up taking nominally healthy individuals of a certain age and then follow them over time?
Yeah, that's right. All 3 of these are longitudinal studies. As my understanding is that the exclusion criteria was if they had heart failure in their diagnosis in advance, that they were excluded. So here they're really trying to get at incident heart failure. What are the predictive markers that help us identify that heart failure is going to happen?
I see. And so as far as it skews older, right? So we're getting We're getting an older group of individuals, regardless.
That's right.
I mean, meaning they're nominally healthy, but oftentimes they have just any different kinds of conditions other than heart conditions.
So it depends upon the cohort, right? So the other two cohorts, as Sarantis mentioned, are the extremely famous Framingham Heart Study, right? And again, that was a community study that was based on residents in Framingham, and that group's actually in their 7th exam. That has been going since 1948. So wow. I remember when they were first using genetics in that study and some of those first publications that came out there. There's some pretty impactful stuff that comes out with Framingham.
If I understood correct also, since there was not any diagnostic method, right, at the time, the 0.0 is entering the hospital with heart failure, right? If I understood correct. And then this is the diagnosis of the heart failure.
For the subset of samples in this study, right, but not the full Framingham study.
Okay.
But yeah, so in Framingham, there were 191 cases and a matched set of controls. So they would refer to this as a nested case control design because it's nested within the larger cohorts that these samples were identified and then matched. And again, what a phenomenal resource to be able to have so many cases and so many controls or so many individuals in a cohort to be able to match those controls as well as they were able to. And then the third cohort that you mentioned was the ERIC study. And this, I think, is really exciting, included in here because it's over 30% of African diaspora individuals. So individuals that are declaring their ethnicity in the study as Black, which I think this is incredibly important for us to understand what we've been missing by the overrepresentation of Northern European populations in studies around heart disease.
And the data for heart disease among the Black community is much higher, right? As far as heart failure goes?
Yes, that's my understanding. And certainly, we have lots of findings that we would never have seen. PCSK9 is one example of them that we wouldn't have seen had we continued to look at European populations.
Right.
So this just double clicks on that. What we've said several times is this importance to not lag behind in understanding omics around these important diverse populations as we go forward.
Yeah. You mentioned something about the Framingham cohort, that this was the 7th examination. So
right. So it's actually the kids, the offspring of the
That's what I was getting at. Right. 1948 is like, they'd be pretty old.
Yeah. Yeah.
Not many people are still around.
Yeah, that's a very important, the progeny of that original.
Framingham Heart Study then is on the 2nd generation of the original people. Is that correct? Or did they take?
That's my understanding.
Okay. So they have the genetics of the parents and now they're looking at the offspring.
Yeah.
Wow. And then the 7th examination was 1998 to 2001, so that they were taking blood samples and full medical workup of all the children.
Yeah, that's right. And actually, there's a comment in the paper about the Framingham participants being a little younger than the other two cohorts. Yeah. By about 10 years, I think, on average.
I'm trying to imagine what it'd be like to be the son or daughter of a Framingham volunteer. It's like, Mom, you did what? I have to do this because you signed up in 1948? Well, are they doing the next generation after that?
Yeah, it's a good question. I don't know. I think
there is. It's one of these, there's so much interesting data, right?
Yeah. Absolutely.
Oh, yeah. Absolutely. Yeah, and having them nested within families tells us so much about what's passed on from parent to offspring. And, genetics we think of as kind of static, and then these other biomarkers dynamic over time. I think if we could just run all samples in that Framingham Heart Study from the beginning to now, imagine what we might learn just with the broadest look.
Yeah.
At the proteome.
Yeah.
Speaking of which, let's talk about the proteins that were looked at in this study.
That's a good point. I mean, I would have expected to look a little bit broader, to be honest, and something that they mentioned at the discussions, right? That they should have gone a little bit more exploratory. I think they used the targeted panel cardiometabolic.
I think that was what was available at the time, right?
Yeah.
So over time, just like I always compare these genetic, my frame of mind is genetics, right? But over time, the first broad scale tools to look at SNPs were around 1536, right? So being able to expand that to 1 million or 5 million on these chips that are available today is just a representation of advances in innovation. And I think we've seen that obviously, here in Olink, in proteomics. So I would love to see a publication around an even broader look at the proteins. And I think with what they've found here, especially with the value of this cohort, that perhaps that's something that they're thinking about. It would be great to talk to them and ask them.
Yeah, I think the HT now, it will be a great
that's right. Yeah, you want to tell our audience a little bit about our latest broadest look at the proteome?
I think Dale can do it better than me at this point, right, Dale?
Yeah, he's been developing all the content.
I'd be really interested, Sarantis and Cindy, to hear your sort of input on this, right? Because I was a person behind the curtain rolling it out. I'd like to hear both of you describe it in your own words.
Okay, Sarantis, you first.
I mean, I will say it in a very simple word. I mean, it's like revolutionize the high-throughput proteomics, right? It's the ultimate tool and assay to go exploratory. We offer like more than 5,000 biomarkers that came out from artificial intelligence, from public research, from key opinion leaders, voice of customers. We are really at the age of proteomics. And then we offer this great tool for people to explore and identify novel biomarkers in any disease now. I think it's the ultimate assay in the field of proteomics. And also, we offer it in a very efficient high-throughput manner. It's really adjustable to the new generation sequencing capabilities, right? And this is make it the ultimate weapon. I would say I'm really proud. I'm looking forward to see the first data coming out of this. That in a nutshell, how I see it, right from outside.
Yep.
But
it's great.
For sure, you have a better.
Cindy, you want to add to that?
Yeah, sure. So what I'll add is that one of the elements that Olink has integrated into this new product is the ability to ease the workflow. And the way we've done that is by, instead of having a very disease-focused organization of the panels, and when I say panels, I mean, subsets of proteins that make up, for example, our Explorer 3072. Rather than being disease-focused, we instead are focusing, and we've talked in here before about how many proteins we cover in the low-abundant proteome. So those are ones where we're measuring them in a neat fashion, meaning one-to-one, we don't dilute them at all in order to discriminate between diseased and healthy individuals. And so we've organized them, rather than organizing them by cardiovascular, oncology, inflammation, or neurology, we're organizing them by dilution block, right? And so we've been able to really streamline the workflow as a result of that. And groups that I'm talking to that are doing large numbers of samples in this population health space can triple their throughput or their capacity with a very modest investment in automation. And of course, at this scale, we're an automated platform controlling beginning to end the processing of the samples in an Explore environment. That said, I would not expect us to sit back on our laurels in trying to cover as much of the proteome as we can in this targeted fashion. Of course, we launched the NGS platform in 2020. We doubled that number of proteins in 2021, and now we're almost doubling it again. So it is, like you say, Sarantis, I'm very excited and very proud of what our R&D team has been able to accomplish in a very short time from my perspective.
And building for that scale, even this particular paper, right? The Homage cohort had 560 cases and 870 controls, right? That's 1,300 samples right there. And right, people's heads just kind of like, wow, that's a lot of work to do, right? 13 microtiter plates. And then Eric had 250 cases, 250 controls. That's another 500 on top of the 1,300. And the framing had about 400. And so that's, okay, what are we now at? We're at 1,400 plus 500 is 1,900 plus 400 is, 2,500 samples, right? Just say that's a lot of work for someone. And yet for the Olink Explorer HT, right, it's built for this kind of scale in terms of scaling the number of samples and being able to finish projects really efficiently with an NGS readout. So super exciting, right, in terms of what our customers and what the scientific community will be able to discover. With this particular paper, right, it was only using 396 plex target 96 panels. And you say, well, yeah, it was only then. Years ago, it was like, yeah, that's amazing to do 260, 270 proteins at a time. But then you think, well, we'll up that by, is that a factor of 20 to go from 270 to over 5,300? Then it's just, wow, what can you do with 20-fold times the biomarkers?
Yeah, or the potential biomarkers to then narrow it down to the ones that are the pathways of interest, right? Because that's the dream. The dream is to be able to make discoveries as broadly as possible and then narrow down to a panel, a subset of proteins that are going to really improve your ability to predict heart failure, right?
Yes.
Above and beyond clinical factors being used today, like NT-proBNP. They talked about in this.
Yep.
In this
and
paper.
that is right what the whole goal of the research was, right? The whole goal was to improve prediction. So, Sarantis, how can you comment then on what they found?
I mean, they found 142 proteins, like potential biomarkers connected to heart failure disease. Of course, in order to be classified like biomarkers, they need a lot of mechanistic studies that they need to follow up. They mentioned that they don't know if some of the proteins that are a cause or an effect of heart failure, right? They need to do some studies in mouse probably, or some follow-up studies. But the important thing that is among these 142 proteins, there are 8 proteins that they are common in all of these 3 cohorts. And among these 8 proteins, of course, natriuretic peptides that were there, something that was expected to be. And something that popped up to my mind, and we were discussing before, was like the eukaryotic translation initiation factor, the 4EBP1 protein. It's a really interesting protein that because it's involved in stress and metabolic stress, and actually binds at the 5' of mRNA, and they block the translation of mRNA when we have a metabolic stress. And it's also regulated by mTOR. And I know that Taylor had a great story about rapamycin, and if you would like to share, I think it would be great because mTOR is a target of rapamycin, and rapamycin is a really famous, actually, drug.
In the aging space,
like the aging factor.
Dale.
Yeah.
Very interesting.
Well, it was about a year ago. I was at a user group meeting for Olink, and a professor from Institute of Systems Biology named Nathan Price was there and gave a really interesting talk about the wellness and the whole markers of wellness and the markers of sort of illness in that transition phase. It was just they're mining data from a startup company called Aravel from years ago that they published several different papers using Olink technology, and they continue to. Well, anyway, about a few months later, he and Lee Hood, the founder of ISB, published a book called The Age of Scientific Wellness. And so me being curious about, well, I wonder if there's Olink data in this particular book on longevity and wellness, I went ahead and read it, and it just blew my mind, right? With the different research on sirtuins, on mTOR, and mTOR in particular was interesting because they talked a little bit about rapamycin and the ability of rapamycin as sort of an anti-aging longevity compound. I mean, I'm like, what? I remember reading about mTOR as being this sort of master regulator, what have you, but to include it in aging? Well, fast forward here to just a few months ago, and I'm listening to a podcast by Paul M. Cooper called The Fall of Civilizations. And it's about, history, and it's about different places and different peoples that I'm not very familiar with. And there was one podcast on Rapa Nui, which was Easter Island. And they basically call it a collapse or a contact between civilizations. But it was on Rapa Nui that rapamycin was isolated from. It's inside a volcano on Easter Island in the Pacific Ocean, where scientists collected an unusual specimen, right? They thought, okay, well, this looks like an antibiotic, right? In terms of the way it was growing. So they took it back. I think it was a Canadian group that ended up isolating rapamycin. And then naturally, right, the biology of it, mTOR is the mammalian target of rapamycin. And it's completely off-label, right, for people to start taking rapamycin just for longevity benefits. It's a crazy world once you get into the whole longevity, aging, wellness business. But the science is rapidly catching up, right, to do away with all the charlatanry that is going on or has gone on. But nonetheless, when I saw, 4-EBP1 in this particular paper as being a significant biomarker, and then Sarantis, you tying it back to mTOR, mTOR being an effector, right? A regulator of this particular.
Phosphorylates.
Yeah, phosphorylates 4-EBP1. Think, yep, biology is a system. And it's all connected. And as far as these biomarkers, though, what can you tell me then about, Sarantis, about the C index that they refer to in the paper?
Yeah, I think the C index is similar to AUC, as far as I understand, like area under curve, and actually defines the prediction, actually how accurate would be a prediction for a model, right? And the really important thing that they see here, and is the fact that when they compare or when they add this proteomic signature to the clinical model, they see a delta C index increase. And that was because it was more accurate at the model. And actually, it was increased even more compared to when they add the typical factors, the typical biomarkers, like the natriuretic peptides to the clinical factors, right? And there was even larger increase. That means that adding proteomics to already existing, diagnostic tools enable and make the diagnosis a little bit more accurate than before. At the level of they see the increase from 5.9% to 11.1%. That is clearly significant.
So it's a performance metric.
Yeah.
It sounds like, yeah, that's really helpful. Yeah, because I was looking for AUCs on here, and I see the delta, this delta CI.
The C index, right? I'm looking.
Yes, sorry, C index.
Yeah, looking at Figure 3, they show the increase, right, in the C index, from what I understand, and
concordance index,
this
right?
concordance
Is that right?
index, yeah.
Okay,
and it's roughly the increase of 10% from 77 to 88, from 73 to 79, from 74 to 81. So these are pretty nice jumps in the C index value when you add the biomarkers. Now, a simple question, was it a lot of biomarkers? Or was it just the 9 that they identified?
No, there was these biomarkers that were selected among these 142 that they were identified in 3 cohorts, right?
Oh, so it was all 142?
I mean, they say that they exclude some of them in the analysis, but it was among these 142 for each of these cohorts, because you see that they have classified, in the Figure 3, they have classified the 3 cohorts.
Yes.
And they have seen what is in each cohort, what is the difference, right? And then there's specific biomarkers in these cohorts, yeah.
Yeah, I see.
And they pointed to, right, the inflammatory pathways as well as the remodeling pathways. They called them mechanistic clusters related to these broad categories, which, inflammation makes a lot of sense. I think this idea of extracellular matrix and apoptosis. I think that sort of points back to your linking this to mTOR, Sarantis. And remember, we talked about the Emperor study in a previous podcast, and some of those pathways they commented in their paper might be linked to some of these, sirtuin pathways. So, I will say the complexity of proteomics is broad, and so just I find these anchors that I'm trying to hold on to start to understand the mechanistic biology behind some of these diseases that are, frankly, the body's so good at using these chemicals in various different organs. We don't have, one smoking gun in any given disease. And so starting to try and put these things together is going to require some machine learning and some. And
so this idea of, predicting heart failure, you have underlying, the first take home was inflammation, right? The inflammation, TNF and other inflammation related proteins and interleukins. Yeah. The other big take home was remodeling, right? And this is what Cindy is talking about in terms of, even before a person has heart failure, there is apoptosis happening. There is hints around autophagic flux, which is the SLGT2, the Emperor study points out. And then, of course, is the possibility of, this is with the lens of only 270 proteins, right? They only use 3 target 96 panels. I say only, right?
Still a lot.
Still a
lot. A lot of proteins.
And still, 2,500 samples. So still a lot of samples and some significant findings, which is what makes this paper so tantalizing, right? To say, okay, we've got a very good snapshot of inflammation. We have hints on remodeling, right? As well as, I think one of the things, they ended up just remembering the figure we were just talking about, right? They're looking at all the proteins specific to the cohort. It made me think, perhaps there just wasn't enough high signal when they narrowed it down, right? They lost that impact of predictive power. But nonetheless, this is the first snapshot. Any other good take-home messages here?
I would say, they talk about, the promise of predictive tools in order to pave the way for design of predictive or preventative trials, right? Like the vision of being able to have these preventative trials, especially when we have imperfect therapies for heart failure today, which I really appreciate them clicking on that. That's one of the last points they make before they go through some of the limitations that Sarantis commented on earlier. So I think that's exciting.
The world of prevention, right?
If only.
Yeah. So many different ways. And if, so I've gone on this sort of hobby now of reading a lot of wellness and longevity books. Really, really interesting stuff. Why? Because the science is catching up, right? Yeah. And the science is now looking into longevity and aging, right, as a separate discipline. So maybe we'll talk about in the future.
I was just noticing that that Peter Attia's new book is now on the top 10 bestsellers list. And I was mentioning that in a group at a conference where I was at in Melbourne. A group of 4 people, we were standing around saying goodbye, good meeting, heading to the airport. And I mentioned that book, and somebody reached into their backpack and pulled it out.
And it's funny you mentioned that book because I just finished it. It's called Outlive.
Awesome.
Highly recommended. Highly recommended.
Peter's podcast is fantastic as well, and he talks quite a bit about rapamycin as well.
And on that note, hey, great to see you all.
Thank you. That was great.
Yeah. Take care.
Hope you're having a good summer. Enjoy your summer. Take care.
All right. Bye-bye.
Thank you for listening to the Proteomics in Proximity podcast, brought to you by Olink Proteomics. To contact the hosts or for further information, simply email info@olink.com.